Let's take a look at example 4. We're asked to find the area of the region bounded by the graph of y equals 1 over x, the x-axis, and the vertical lines x equals to 1 and x equals to e. In any kind of problem that's of this form where they ask you to find the area of a certain region, it's always a good idea to do a rough sketch of the region first. So the graph of 1 over x would look like this. The vertical line, x equals to 1, would be roughly here. X equals to e is bigger than 1, so e would be to the right of it. The x-axis, we know that that's this line right here. And if we look at the region that's bounded by it, we're referring to this region right here. So we want to find this area under the curve. We can use a definite integral to do this. The area is going to be equal to the integral from the region extends as far left as 1, as far right as e, and it's the area under the curve of 1 over x dx. We can use our fundamental theorem of calculus. The antiderivative of 1 over x we know is the ln of absolute value of x. We're going to evaluate that from 1 to e. This is equal to the ln, the absolute value of e, minus the ln, the absolute value of 1, which is simply going to be the ln of e minus the ln of 1. The ln of e is 1, the ln of 1 is 0, and so we would get that the total area under that region would be equal to 1. Let's take a look at the mean value theorem for integrals. We had a mean value theorem earlier for derivatives. Theorem 5.10, which is the MVT for integrals, says that if f is continuous on the closed interval a to b, then there exists a number c in the closed interval a to b such that the definite integral from a to b of f of x dx is equal to f of c times b minus a. To try to get some intuition for exactly what's happening here, let's take a look at the following. So let's suppose we have a continuous function, and suppose we have this interval a to b, which is closed. And I'm going to draw a function in that interval. The left-hand side of this MVT represents the area under the curve. Essentially, what they're saying is that if f satisfies the values of the mean value theorem, then somewhere in there is a point C, such that if you look at the rectangle whose height is f of c and whose width is b minus a, in other words, left width of the interval, that you can find kind of a point where the area of that rectangle would be equivalent to the area of the under the curve. This also allows us to define the average value of a function f. If f is integrable on the closed interval a to b, then the average value of f on the interval is defined by the length of the interval, that's 1 divided by b minus a, times the definite integral from a to b of f of x dx. So it's essentially taking the value of the definite integral and dividing it by the width of the integral of the interval, which is b minus a. Let's find the average value of the function f of x equals 3x squared minus 2x on the interval 1 to 4. So the role of a and b is being played by 1 and 4. This should be 1 divided by b minus a times the integral from 1 to 4 of 3x squared minus 2x dx. 4 minus 1 gives us 3, so it's going to be 1/3 the definite integral from 1 to 4 of 3x squared minus 2x dx. To find that definite integral, we're going to find an antiderivative for the integrand. This is going to be 1/3 times, again, we're going to use our power rule, add 1 to the power, divide by the new power, but that antiderivative should be x cubed minus x squared, and then we're going to evaluate that from 1 to 4. This is equal to 1/3 times, we have 4 cubed minus 4 squared minus 1 cubed minus 1 squared, which is going to be equal to 1/3 times 4 cubed is 64. 4 squared is 16. 64 minus 16 is 48. Over here, 1 cubed is 1. 1 squared is 1. And 1 minus 1 is 0. So we get 1/3 of 48 minus 0, which is 1/3 of 48, which is equal to 16. So we would say that the average value of the function f of x equals 3x squared minus 2x on the interval 1 to 4 would be equal to 16.